Questions about anything? Well, today I'm going to talk about an important subject, namely isolated singularity of analytic functions. And that's going to pave the way for us to do the residue theorem next week, which is one of the big applications of this subject to science and engineering. It's kind of fun also. Also, it gets used in theoretical math contexts because it's a way of computing integrals, and many of the integrals came up in history in very important places. So it's a powerful tool. But to get started in that subject, it's important to note there's exactly three kinds of isolated singularities. So I'll call them types. I mean, real functions can have all kinds of wild and crazy different kinds of singularities. There's sort of no limit to how weird you can make them. But analytic functions can only do exactly three things. And the observation is based on the... now we know that if a function has a Laurent expansion. So Laurent expansions were for on an annulus. But if the thing is analytic all the way down to a point z0, you can make that annulus shrink down to z0. So this green one is the outer one, and the blue ones are the inner. Anyway, you can make that shrink down to z0. And of course, they all have the same Laurent expansion. The coefficients are given by integrals, which are all the same. Integral around some circular thing inside there. And so that Laurent expansion is valid on the whole punctured disk. So what we know now is that F can be expanded in a Laurent expansion, which is the sum as n goes to minus infinity to plus infinity of a n z minus z0 to the n. And it converges absolutely on every point in that punctured disk. Well, there's three possible cases based on looking at that series. One, maybe the ANs, all the negative ones, they're the scary ones. So first possible case is all the ANs are 0 for negative n. For all negative n. Then in this case, z0 is we're going to see that z0 is a removable singularity. In this case. And I'll explain what that means. It means I can give the function a value at the point z0, and it becomes analytic on the whole disk. So in that sense, it's removable. And I showed you an example of such a thing last time. Okay, and the reason is f of z is equal to its Laurent expansion, and its Laurent expansion would only have this piece of it. And that piece is just a regular old power series. And we know power series have a radius of convergence. So it has a radius of convergence bigger than something. And so it converges to an analytic function on a disk. So let's call radius of convergence. Actually, that radius of convergence would be r, and it would be greater or equal to the epsilon. And so it converges to an analytic function. On the whole disk. And so we see that if we give, what should we give the value of f at z naught? We should give it the constant term in that Taylor expansion. So the if we set f of z naught equal to the a naught in that series, then f is analytic. It becomes analytic on that whole on disk. And that's what it means to be removable. I just removed the singularity by giving the f the proper value. Okay, that's one possibility. Any questions about that? The second possibility is that there's only finitely many negative terms. Negative terms. Let's say that, I didn't want to start that just yet. I wanted to make let me move this down. I wanted to make a couple remarks about removable singularities before I do that. So let's see, last time I showed you an example of a removable singularity. It was sine z over z. And I played around with power series to that. That should be 0 no, it should be 1. That's the famous limit. So I talked about that last time. That's an example. And so here's the fact. That z naught is removable if and only if the limit as z tends to z naught of f of z exists. In all the other cases I'm going to show you, the limit doesn't exist. It either blows up or just goes totally berserk. So this is the only case where that limit would exist, and that happens in the case of a removable singularity. And we're going to see there's a famous theorem called Riemann removable singularity theorem. That happens if and only if f is bounded. On, let's say, a disk of radius rho about z naught minus z naught for some epsilon. I mean, for some rho with 0 less than rho less than epsilon. That's going to be a theorem. but it's worth pointing out at this point because it'll help you give you a feeling for what that means. So these are facts. Okay, if there's only finitely many negative terms, then when we write out the Laurent expansion, we get, let's say there'd be the first negative term that's not zero. Let's call that a sub minus n. And then there'd be some more terms, et cetera, et cetera. There'd be the last negative term would be the negative 1 term. That would be over z minus z naught to the 1. And then the rest is a regular power series, plus a naught plus a1 times z minus z naught plus dot, dot, dot. So this part's a regular power series. So it would be analytic on the whole disk about z naught. And this is a rational function called the principal part. This is a rational function which we're going to call the principal part. The principal part of f at a pole. This thing is going to be called a pole in this case, at the pole z naught. Okay, and here a naught, a sub minus n is assumed to be not be zero. Assume a sub minus n is unequal to 0 is the first non-zero term. Non-zero negative term. And z naught is called a pole. And the pole is said to be of order n. Kind of like we have orders of a zero, we're going to have orders of a pole. And they're kind of similar in a lot of ways. Of order n. And here's, if you think about what that's going to mean, let's think about loud for a second. If I multiply that Laurent expansion by z minus z naught to the n, I clear all those fractions. So if I multiply z minus z naught to the n times f of z and multiply through that Laurent expansion, I'd start out with a minus n term. That would be a constant term. And then the next one would be a minus n plus 1 z minus z naught plus dot, dot, dot. And we'd have a naught times z minus z naught to the n plus dot, dot, dot. That's a power series. And so, of course, it converges on the same z's that the Laurent expansion did. That's a regular power series. With a positive radius of convergence. It converges to an analytic function, capital F, let's call it. And let's see, that would be, it would have the same radius of convergence as the series, Laurentian series. Well, I say it converges to an analytic function of f, and it would converge on the disk of radius epsilon about z naught. Pick a z in there, it would converge, and so we know the radius of convergence would be greater than or equal to epsilon. And notice that f at 0 is an. Not f at z naught is equal to a sub minus n, and that's not equal to 0. Okay, so in fact, we see that because of that, we can write f of z equals capital F of z. I guess this is just like the 0 business. I would have here z minus c naught to the minus n. So if it was a 0, that would be a plus n. If it's a pole, it's a minus n. So interesting to note, very similar to the looking to a 0 of order n, except there's a minus n where the plus n should be. So it's very similar to a 0 of order n, but with minus n where the n should be. So in a lot of ways, the work is dealing with the pole is very similar to thinking about zeros. And another important fact, a consequence of looking at this formula, the limit as z tends to z naught at a pole of f of z is infinity. And in fact, that's the defining feature of a pole. This is the defining feature at a pole. It happens exactly when the thing blows up to the point at infinity at z naught. And I showed you an example of this last time, something like sine z over z to the fourth has a pole at z equals 0, because I can write the power series for sine and when I divide that by z to the fourth and distribute it through, the first term would be 1 over z cubed. Second term would be minus 1 over 3 factorial over z. And then the next one would be plus 1 over 5 factorial times z to the 1 power plus dot, dot, dot. This is the principal part. And this thing turns out to be entire. An entire function. It has a power series that converges for all z. That has a pole of order 3. At z equals 0. And now finally the case 3. The last possibility is, well, if their first possibility was all the negative coefficients are 0. Second one was finitely many are not 0. And then this one, it's going to be there's infinitely many non-zero. So infinitely many non-zero negative coefficients.
Well, does that dictate how fast it dives?
Yeah, the bigger the n, the more it blows up to a greater order of blowing up. It's like the opposite of an order of a zero. They shrivel up really fast, but in this case, in a pole, they would blow up really fast. But it's still a finite order, so it's, yeah, so the example I showed you last time was e to the 1 over z. That has a Laurent expansion 1 plus 1 over z plus 1 over 2 factorial 1 over z squared plus blah, blah, blah. There's a constant term, but all the rest of the terms are negative powers of z. And that shreds the complex plane. I showed you how bad it can be. And in fact, that turns out to be a general feature of essential singularity. So I'm not going to demonstrate this fact in this class, but there's a thing called Picard's big theorem. There's a Picard's little theorem too, which is related. Picard's little theorem is about entire functions, but it's quite related to Picard's big theorem. So let's suppose f has an essential singularity. At, say, z naught. Let's say that f is analytic on a little punctured disk, d epsilon about z naught minus z naught. Then, for any row bigger than 0, no matter how small, let's see, for any row with 0 less than rho is less than epsilon, no matter how small, F maps this little tiny set. Let's see, it's d rho of z naught minus z naught. It's not defined as z naught. Infinite to 1, just like the e to the 1 over z did. Infinite to 1. So that's pretty nasty. On to c, with the possible exception of missing one point. So on to c with one possible missing point. And that's, you think, like e to the 1 over z misses 0. It hits everything else infinitely many times. Misses 0. Some things don't miss anything. But e to the 1 over z shows you that it might miss something. So that's Picard's big theorem. And it characterizes the behavior at an essential singularity. So here's a typical example you'll find in the homework. Example. Let's think about what kind of singularity does cosine 1 over z have. at z equals 0. Well, there's only three possibilities. Let's try to rule them out one by one. So if you think about, could it have a removable singularity? Well, then it would have a limit as you go to 0. And if you think about for t real, we know what cosine 1 over t looks like. Cosine 1 over t is bounded by plus and minus 1. Is bounded by 1 in absolute value. And it wiggles like hell. As t tends to 0. That means that cosine 1 over z couldn't possibly have a value. Can't possibly have a limit at z equals 0. So cosine 1 over z couldn't possibly have a limit as z tends to 0, because it just goes totally bonkers on the real axis. And so that's not, the singularity is not removable. Not removable. And for the same reason, it can't blow up to infinity either. So similarly, cosine 1 over z couldn't blow up to the point at infinity either. Because it's be dragged down along the real line and be something bounded there. It has to go to infinity and the whole punctured disk to go to infinity. So it's not a pole. And so that leaves us with the other possibility, the last possibility, it's got to be essential. So we've ruled out the other case, and so it must be essential. And in fact, it's easy to write out the... so I didn't have to do anything here. I didn't have to write out a Laurent expansion, but it would be easy to do that. I know the power series for cosine, and I'd just stick 1 over c in it, and I'd see it has infinitely many negative terms. But sometimes you can deduce these things without even looking at the series. Yeah, question?
So this is essential is the third singularity, the third type that you talked about?
Yeah. That's when it goes totally ape. It's not a pole, it's not removable. Let's see. Like alluded to this famous thing called the Riemann removable singularity theorem. It's stronger than just having a limit at the point. So it says that suppose f has an isolated singularity. So f is analytic. And bounded. on some little disk, punctured disk, and bounded on disk of some radius epsilon about z naught minus z naught. Then z naught is removable. That's way false in the real case. For example, sine 1 over t is bounded. On minus epsilon to plus epsilon minus 0. But 0 certainly is not a removable singularity. It just goes totally bonkers, and you can't give it a value at 0. So it's something very special about analytic functions. Let's see. Here's how the book demonstrates this fact. We could prove this with very carefully and correctly without using Picards. The book demonstrates this fact using Picards. So here's the simple proof. I could do this without using Picards. But that's like using a sledgehammer on this thing. Okay, so it's just like that problem I just did with cosine 1 over z. If it's bounded, you rule out a pole. So bounded means it can't be a pole. Bounded, so not a pole, because poles blow up. And bounded, so it can't plaster the whole complex plane. Bounded, so it can't plaster the whole complex plane, as in Picard's. It can't plaster C, as in Picard's big theorem. And so that rules out those two possibilities. That means it must be removable. Okay. Let me just make a remark. I'll probably do it at some point later. Here's a proof without Picard's, which I'm not going to show you all the details. Think about it. Proof without Picard's. Let f of z equals z minus z naught squared times f of z. If z is unequal to z naught, let's see, let me move this. So it's going to be equal to f of this if z is unequal to z naught. And guess what? Since f is bounded as z tends to z naught, that's going to have a limit at z naught. Its limit's going to be 0. Show f is analytic. Show capital F is analytic on a disk. about z naught. And then use power series to see f of z has a 0 of order 2. And then when you divide by z minus z naught squared, you'll see that f has f is equal to a power series. And you'll be done. So that would be a rigorous proof that doesn't use the killer theorem of Picard's. But the reason I'll blast ahead and keep going is because I want to do the residue theorem really bad. So I can use it next week to do some great examples. So let's see an important definition. The a minus 1 term is really special. A minus 1 in the Laurent expansion is called the residue. Of f at z naught. And we'll write a minus 1 equals the residue at z naught of f. And we know that, let's see, note, there's a formula for this residue theorem, and this residue. Let's see, what is the formula? It's a minus 1 equals the integral over a little circle of f of z the power of the z minus z naught that I was tempted to write in the denominator there is 0. Because we had this general formula that worked for all the n's. A sub n was equal to integral around a circle of radius z naught, a row about z naught, of f of z over. It was the same as the power series formula, except the n's were allowed to be negative. Okay. When the n's are positive, you get the regular power series formula. And you can use the oops, I forgot something. There's a 1 over 2 pi I here. My teacher said, from now on, we assume that 2 pi I is equal to 1, because he kept doing that all the time. Let's see, so when n is positive, that's just the higher order Cauchy formula for the Taylor coefficients. But when n is negative, that's something new and different. And in fact, when n is minus 1, then that thing in the denominator is z minus z naught to the 0th power. And that's kind of the baby residue theorem. So I'll call that the baby residue theorem. Is that we have the residue theorem on a disk, and it says that if I want to calculate the integral of around my singular point of f of z dz, then I can solve that for the integral, and I get 2 pi I times the residue at z naught of f for small circles about the singular point. C rho Z naught. They've got to be counterclockwise about the singular point. It turns out if you have a baby residue theorem, then you get a big residue theorem. And I'll show it to you soon. Let's see, you have one homework problem that kind of demonstrates why the residue is important. So let me explain why it's an important number. Let's suppose I'm going to demonstrate this by an example. Let's suppose f of z, I'll make it have a pole. So I'll make it start out at an over z minus z naught to the n plus a sub n minus 1 over z minus z naught to the n minus 1 plus dot dot dot. I have an a2. I'm going to want to move this. I'll have an a2 over z minus z naught squared. And then the residue term, a1 over z minus z naught. And then I'll have a g of z that's entire. That would be the power series part. So this is going to be entire. And if you look at that for a minute, you realize that every one of those terms in that thing is the derivative of something, except for this one. This is the residue. Okay, and this one is the derivative, that's d by dz of an times z minus z naught to the minus n plus 1 divided by minus n plus 1. It's the derivative of something. And so is that next one, and this one is the derivative. That's d by dz of, what is it? a2 over z minus z naught. Minus that. Okay, and so if I was going to calculate an integral, if I take, say, a contour like this, which is a very typical thing to do in the subject, let's say this is the real line, and my z naught is, say, right here, inside here. Let's call that curve gamma. Well, then my integral around gamma of f dz, the integral of around something that's a derivative would be 0, because it's a closed curve, and I'm doing and by the fundamental theorem of calculus. So I get 0 plus 0 plus 0. And then the one that would be not 0, perhaps, is the residue term. And then the integral of the entire thing would be 0 by Cauchy's theorem. So these zeros are because of the fundamental theorem of calculus. Those terms are derivatives. So that's the fundamental theorem of calculus. The entire function, that's just the Cauchy theorem. And so the one thing that's not 0 is that term right there, and that's equal to 2 pi I, this one right here, is equal to 2 pi I times the residue. We know that integral We've used it a lot previously when getting the Cauchy integral formula, etc. In fact, that's the Cauchy integral formula with f of z equal to 1. So this is the Cauchy integral formula using f of z was a1. And so we get the thing is 2 pi I times the residue. And if there was more than one singular point, I would get more than one term if adding up the residues. 2 pi I times the residue at z naught of f. So even though there was a baby residue theorem above, we get kind of a big residue theorem out of it if we think about it the right way. And that explains exactly why that's the relevant term in computing these integrals. All the other ones can be seen to be 0 for some reasons, like fundamental theorem of calculus or just the Cauchy theorem. So next time I'll do it carefully, but I can show you sort of the big picture for the residue theorem that I'm going to do next time. The big idea. Let's say I want to do the residue theorem for some curve gamma, and I have finitely many singular points. So I'll have a z1, a z2, and a z3. So this thing is going around counterclockwise. And we've seen this idea before. I would punch out little circles about these things. So this would be the only singular spot in there. And let's see, I'm going to make those things go clockwise. We'll see that that's a good idea in a second. And then I'm going to take cuts. Let's see, cuts are going to go this way on top and this way on bottom. This way on top, this way on bottom. This way on top, this way on bottom. And last one, like this. Then when you look at that, and so if I were to add, I have an F analytic inside and on gamma with singularities at the z's. So singularities at the z's. The zj's. Then when I add up those integrals, I get a top half and a bottom half. And when I add them up, I would get the integral around the top half plus the integral around the bottom half of f dz. When I add them up, I'd get the blue part. That would be the integral around gamma of f dz. That's usually the part I want. And then the pink cuts would cancel because they're going in opposite directions. Those integrals would cancel, and I would get all those other ones would be minus. So I'd get minus, let's call this one radius rho 1, this one rho 2, this one rho 3. Those are going clockwise. So those would be minus a sum as the j goes from 1 to 3 of the integral around c rho j